Okay, so we're looking at a very simple circuit with a piece of uniform nichrome wire and a battery that holds the ends of the wire. At two different voltages, okay? So it's like we got V1 and V2. And we got some length. Now we could draw the battery source in series with this, but I'm not going to do that. I'm just going to isolate this thing and say we got some voltage here, some voltage here, okay? And it's uniform. And then we put a couple of leads here. And we want to ask ourselves, what's the okay, well, I'm having a notational meltdown here. I want to use delta V for the potential difference here. I don't want to use it here. So we're just saying potential difference equals what? If this distance is let's just say D, I'd like to use D. There it is. Okay. This distance is D. What's the potential difference between here and here? Well, let's go ahead and put the length in here. Potential difference is D over L times delta V, where delta V is potential difference from here to here. Now, I'm not being particularly careful about the sign of the potential difference. In the first place, I don't know if V2 is bigger or V1 is bigger. I don't care. Just the magnitude of the potential difference would be fine. Okay. So just to be being more rigorous, I'll put absolute value signs around this delta V. Now the sign does matter, but the concept is very simple. This is a concept we're trying to get to that people had a little trouble answering. Okay, even though we investigated this in lab. So you want to kind of think through that. And I ask you then to explain this, and we talked about it, gave an explanation. After I think people saw the whole thing, wouldn't have been a bad idea to draw a picture like this. Pretty much represents it. Okay. Just D over L times delta V. You can see D over L looks like maybe 20% or 15%. Okay. And just multiply that by your change in potential, and there it is. Okay. So some sort of a simple picture, maybe a better one than this, is always a good idea because the picture can remind you of all the important things. Okay. Okay. Now, I then asked, why is the potential gradient between here and here in this situation constant. Well, potential gradient is constant. Because current is constant, no place for charge to accumulate. So what goes in has to come out. What goes into any point has to go out of that point. Okay? Meaning that the current's going to be the same at every point. The cross-sectional area is uniform. So current density is uniform. And you should know the current density is current per unit area. You should also know that you multiply the conductivity by the potential gradient. Okay. Current density being product of conductivity times potential gradient. I'm just mentioning that it's not part of this argument at this point. Just a note to remind you of really important relationships that might not be as emphasized as I would wish on the transition problems. Maybe it is, maybe it isn't. I'll have to take a closer look. Okay. Also current is current density times area. And actually, I'm going to change the parentheses. This is a parenthetical comment, but then the current density is uniform since the current equals current density times area. Okay, and the area is constant. So there's a tight argument there. It's expressed maybe a little bit loosely. Okay, make sure you really understand this. Look at it for 30 seconds every day in your schedule of things to look at until you can visualize it, so you can see it in terms of what you saw in lab last time. Okay. Very important for being able to sort out the conduction model. All right. Now, question. how would this argument come? What would change? The wire gradually widens. No, its cross-sectional area gets bigger and bigger. Okay, I got two really good answers quickly. The first one was, well, the current density is going to change, because that's current per unit area. He said, well, exactly what has to be so to make that true? And he said, well, because the current stays the same. Current stays the same. There's still no place for current to accumulate just because that wire is getting wider. Okay. So, so the answer is the current density changes. Now, what is it that changes? What else changes if the current density changes? Okay, we got another good answer there. Um, Changing current density implies changing potential gradient. Okay. So I don't have much room to draw it. Let's draw a wire from here to here. Okay. Now this is okay. Wire here where it V1, here where it V2. What's the electric field going to look like? Now the electric field of a uniform wire would look something like this. You can imagine a lot of arrows in there, but it's impractical to draw them. Okay. But all the arrows are going to have the same length, indicating the constant vector field. Okay. What's a vector field in that non-uniform wire look like? Okay, we got a couple of good respectable answers. One is that as the thing gets wider, the electric field gets bigger. And the other is, well, by analogy with fluid, if you got a fluid flowing here, it's going to be flowing faster here than it is here. Okay. Assuming this is a closed, well, assuming that you're not losing or gaining any fluid between here and here. So the bottom line is the connection you could immediately make, but you're not as familiar with this stuff as you're going to be. Okay. Connection you could immediately make is that the potential gradient is going to decrease. Okay. And I didn't actually write that down, although that was said. I could say, so the potential gradient decreases with width. I don't know if that's legible, but that follows pretty quickly. Don't strain your eyes. You can always look at it on the, but I said potential gradient decreases with width. Okay, or diameter or thickness. I didn't use diameter or thickness because width was a shorter word and I didn't have much room. Okay. But diameter or thickness would have been a better choice. Then you simply make the connection in the uniform wire. The electric field is constant. And why is that? Because the potential gradient is constant, which we just established. And what is the electric field? It is the potential gradient. Okay. Now, those are concepts. They're not terribly deep. I think they're harder to pull out of the equations to really understand for most people than to understand in terms of something you've had your hands on. Okay. But whichever way you understand it, you understand that that electric field is constant. Here then, since the current density changes with the width, it decreases with the width, same current, more area, decreasing current density. Current density is the conductivity times the potential gradient. And the potential gradient is the electric field. So if you're going to draw the electric field, it's going to be decreasing. Well, that's a multi-step argument. But if you understand the concepts, it should become pretty obvious to you. And it seems like it pretty much is to everybody here. Okay. So you're going to have your electric field here. Going to be getting smaller and smaller. Okay, decreasing electric field. Probably doesn't decrease as drastically as I made it, but you get the idea. Decreasing electric field due to decreasing current density. Current density being directly proportional to the potential gradient, which is the electric field. I also mentioned just inside because it came up, it's conductivity times potential gradient, and conductivity and resistivity are reciprocals of one another. Okay. I'll just take a little note here. Sigma is often used for current density. It's a Greek lowercase sigma. I'll say conductivity times E times the electric field, which is a potential gradient. Okay. Actually, yeah, I think sigma. I'm confusing my symbols here. Sigma is the symbol often used for conductivity. Rho sigma, rho is standard for resistivity. Okay. So that I should look at the equations. I put the current density. Current density equals conductivity times your electric field, which is your potential gradient. And then resistivity is 1 over reciprocal conductivity. Those are things you ought to store away. Because you're gonna need them. You're gonna see them. Okay, now, give you a second to note that. I'll just pause for a second. Okay, same picture as before. So at this point, first of all, let's just reemphasize, let's make sure we've got this, okay. The potential difference between here and here is the same as the potential difference between here and here, right? And we assume this is a conducting wire of essentially infinite or near infinite conductivity, so that there's no potential loss, even if there's a current flowing in this wire. Now, there isn't at this point because there's no place for it to go. This is at some voltage, this is at a lesser voltage because of the potential drop between here and here, right? So you have a potential difference here, and here's what it is. But until you connect a wire, let's say between here and here, there's no place for the current to go. It can't accumulate. So nothing moves. Now, we come over to this situation, and we're going to go ahead and we're going to introduce some length of wire here. And we like to draw things with right angles instead of drawing an incoherent loop. Okay, it's easy to keep track. So I draw it like this. Now, okay, I'm going to start labeling some points. I'll just call this point A. I'll call this point B. I'll call this point C, and I'll call this point D. You know, I've drawn a conclusion. I hate to have to rewrite this. There's something I should say in between there. We said it, you know, we looked at this, at the system. And I'll say, if there's negligible resistance in this thing, whatever we mean by that, that means a whole lot of conductivity, right? Essentially infinite conductivity. Then this point, this point, this point, and this point are all going to be at the same potential. Call this point G and E. I should call this point E. Call this point L. And they're all at the same potential. And I'm going to, if that statement, I'm going to keep it fairly simple. Think about why they're all at the same potential. It's because this is all a good conductor. Okay. So there's no potential loss between here and here. So the current from here to here is whatever current we have from A to B. And that equals the current from C to D. Because if it wasn't so, you'd have accumulating charge at some point. Now, more standard notation. Often you see a lowercase I think in your text for current. I use a capital I to distinguish, to avoid confusion between current and the square root of -1. Okay. A lot of times in electronics, they'll use J for the square root of -1 because they really like to use that lowercase I. Okay, and there's good reason for it. I'm not arguing with anybody, just my choice to use capital I. So if your book happens to use lowercase I, don't let that throw you. Okay, but I'm going to say, okay, I'm going to indicate current. Here's current. IAB. Here's current CB, ICB, BC. Here's current IBC. Here's current IBC. And here's current ICD. And they're all the same. Because there's no potential difference between point E and F. So there's no potential difference between point B and C. Okay. And then you got, then, okay, we'll have current I, B, C. there's no potential difference from B to C. Potential gradient is now delta V divided by L minus D. Remember, L is total length, D is this. You have no potential drop between here and here. So the total potential drop is between A and B, and then between C and D. Which is greater than the delta V over L that we had over here. And that is the potential gradient from here to here, and we multiply. I could have written this as D. Put this in the form D times the potential gradient. Okay. We're just doing proportionalities when we did this. Introducing term short circuit that I used when we were over there looking at it. We could say this then. Short circuit from here to here, if it doesn't blow your fuse, then it won't if this didn't, because you're not going to get more current through here than you have through here, right? But it means you're going to have more current. Flowing in the circuit. And if that connection hadn't gone wrong, we would have been able to observe that pretty quickly. Okay. In a believable way, just complete this circuit here and the current goes up. Again, what we're trying to do is we're trying to think about what goes on in a circuit without referring to a bunch of actually quite simple equations. So when we see those equations, we have some understanding of conductivity, okay, and the essential concept of current density goes quite a bit deeper in those formulas, okay? Still, those formulas are important, and they're not hard to use, so it's not too difficult to take care of that, to deal with that. Okay, now, if this wire that we insert has significant resistance, meaning it has a finite conductivity, so that it doesn't short the circuit between here and here, then we have current branching. Okay, some of the current will go through here, some of the current will go through here, then they join up here and move on. Okay, so let's depict that. So I'm gonna draw this part of the circuit a little more simply. So we have the point A here, we have the point D here, we have the point B here, we have the point C here. And we have then IAB. And here we have some resistance here. We don't have an infinite conductivity in this part of the circuit. So we get I, B, C. And then I, C, D. And then we have an I, B, C here. And now I've got two different parts of the circuit represented by the same thing. So instead of using the A, B, and B, C notation for these two currents, I'll just call this I1 and I2. Well, I1 plus I2 has to equal IB, which is equal to ICD, right? It's called a branch point, and whatever goes into a branch point has to come out of the branch point. There's no place for the current to accumulate, so you have to have the same current here as you have here. So we could just call that I. Okay. I could pose a problem like if this is also nichrome, but it's got twice the diameter of this nichrome, then what are these two? If this circuit, let's say this current is 0.3 of an amp, which is kind of what we've observed with the circuit we're dealing with. We've got 0.3 of an amp here. And I branch the circuit to go through nichrome with 3 times the diameter. How much of the current goes through here and how much goes through here? So I'm just going to pose that as a question for you to think about. I don't necessarily expect a solution instantaneously, but you might get it because we've already looked at something that's kind of similar. So I'm just going to state it. I guess I do need another point here. I'll just call this point here. Call this point E. So the wire BEC goes B to E to C, A, B, C, D. That's the straight wire. You can think of a original piece of nichrome and a piece of nichrome with 3 times the diameter. I think we've got some of that in here. I just can't seem to lay my hands on it. But anyhow, we don't really need it at this point. That's what's the ratio of I2 to I1. That word is removed. What's going to happen if we disconnect this wire? What's going to happen to the current here? Think through that. I think it'll give you a little deeper insight into the nature of resistance circuits. Okay. The other thing I want you to kind of focus on set 1 in electricity this week, okay? So try to get through, like, try to at least read through the whole thing if you haven't already. And then nail at least maybe the first half, at least reasonably well by Wednesday, okay? So we can really start talking about the electric fields and electrostatics and all the neat stuff we can do with this stuff. Okay.